All right, now that we talked a little bit about bubble sort and selection sort, I thought we'd take a little bit of time and talk about a couple sorting algorithms that are a bit more efficient than those two options would be. We mentioned how both of them are pretty much always going to end up being n squared time. And because of that, once you start dealing with pretty large sets of data that you're trying to sort, they're not going to be the best options. So instead, there are actually quite a few other sorting algorithms out there that we could potentially use. And we're going to talk about a couple of different ones that are pretty much quite a bit more efficient than selection and bubble sort were. And the first one we're going to talk about is called merge sort. Now, merge sort is going to operate off of a bit of a different underlying technique than selection and bubble sort did. Selection and bubble sort were both known as what are called in place sorts, basically meaning that there were no extra data structures required in order to actually get your list of numbers sorted. Whereas merge sort is going to be a sort where we actually start allocating new lists and start sorting sublists as we go along, which means it's going to require a bit more memory to use. But even though it's using a bit more memory, the efficiencies we gain by doing that are pretty drastic. Right, so the whole idea of merge sort is that instead of trying to sort one giant list all at once, we're instead going to first break down this list into lots of little sublists, and then once we finally break all of the lists down into individual lists, we'll start merging these individual lists back together and start sorting them as we merge them. And this results in us, by the time we bring everything back up into a single list, having a fully sorted list. And usually this is going to be implemented recursively. Right? So the easiest way to really look at this is if we actually visualize what's going on. Which, hopefully, this loads. There we go. Right, so the whole idea is we're going to start off with this list of numbers right here. And what we're going to do is we first pick a pivot point or a divide point in between that list, which is usually just going to be the dead center of the list. At which point we then take our overall list and divide it into two sublists on that partition point in the middle of the list, right? So we took this big list and split it up into two smaller lists. Now we're going to continue on and continue splitting that list until each sublist only contains a single element. So you can see we took our sublist, found the middle of it, split it. We'll find the middle of this sublist because there's more than one element in it, split it as well, and then we'll end up with two single item lists. And then we do the same for the right side. Right, so now we have four individual lists of various numbers that could be of any order. So now what we will do is we can start taking those four individual lists, or I guess six overall, and we'll start merging them back together. All right, so we're going to end up looking at the first thing here is that each list of one item is technically already sorted, so there's nothing to really do there. So we can go and we can continue and merge our bottommost list. So we will merge 3 and 11 into a single list containing 3 and 11. And then we can look and we'll say, well, those are sorted, and now we can try to merge these two lists together. And you could see that we basically end up comparing each node inside of those sublists to the adjacent node in order to merge them all back together. And as we merge our sublists together, we sort as we go, and we end up with our sorted list. All right, this kind of looks a little funny, this whole merging business, so let's take a little bit closer look at how the merges work as well. All right, so again, we have our two sublists, and effectively, this merging is going to work by keeping track of 3 pointers, or 3 indices into our sublists. We have our first sublist, which we have a pointer, we just call that left pointer. We have our right sublist with an index into it as well, called our right pointer, and these both start at the very beginning of each list. And then we have our current position in the merged list that we want to gain, or that we want to build up. All right, so the first thing we do is we compare our left pointer's value to our right pointer's value and see if they're in the correct order. If they are, then we go ahead and add our current value, or our current left values index, into our final sorted list, right? Because there's nothing else to do with it. After that, we're going to redo the same process again. All right, so we incremented our left pointer. We can compare 8 to 4. We know 4 is less than 8, so we swap that guy up into our final sorted list. And we're going to actually continue to do this over and over again until both of our two sublists are merged together, right? And then if there is another sublist to go along with that sublist, we'll again merge them together as well. Now, the interesting thing to note is that if one sublist is smaller than the other sublist, or if we merge all of the numbers from one sublist into the main list before we merge all of the numbers in the other list, like we had happen here, then we just go ahead and throw up the last numbers, or append the last numbers, to our merged list. And that's just because we can assume that those are already sorted, right? That is a property we get from having sublists that are already sorted merged together, right? In our topmost bit here, our individual lists, or our individual numbers, were sorted in that list. So when we merge them together, we get a sublist of sorted numbers. So here we could assume that whatever's left over in those sublists is in the correct order and merge them up, because they will be sorted again as we continue merging up to our final list. So because of all of this splitting and dividing and all of this kind of stuff, we can really end up basically with a big O time of about n times log n, right? And we get that effectively by saying, well, the division of the list and the sublists is going to take about log n time, right? Because we're dividing things in half every time. We're not iterating over every node. We're just dividing everything in half, right? We've divided our sublist into two lists, and then that list into two lists, so on and so forth, until we couldn't divide things anymore. So that gives us our log n. And then on the way up, we basically end up with a big O of n time, because we effectively compare all of the nodes to the other nodes in the list. Right? So this gives us a big O of n time. By our rules that we saw in the Big O video, then we can just effectively combine those two together to be big O of n log n time, n times log n, which is overall a pretty respectable big O time, or sorting time in general. All right, we're not going to build merge sort in this class, but if you want the extra fun, the extra practice, the full algorithm is here. There is a little bit of code to it. Not a whole lot, but a little bit, just because this is a slightly more complex sorting algorithm. But it definitely has its benefits. And I'm hoping that you're starting to see a little bit about the complexity versus space and time trade-offs. Oftentimes, the more complex things get, the more efficient we can make things. That's not a hard and fast rule, but as you can see from what we've seen so far from our little 6, 8, 9 line bubble sort compared to this 25, 30, 40 line merge sort, the efficiencies between the two are pretty drastic and differ by a fair magnitude. Okay, so just keep that in mind when you're looking at this sort of code. So that is merge sort. If you have any questions, let me know. We'll see you in the next video.